Andy Su, founder and CEO of Semiconductor, company that's focused on the development of innovative architectures for NAND flash and DRAM memory. Andy's responsible for the overall company's strategy, execution, and technology innovation that fuels the company's growth. He has more than 25 years of experience in the semiconductor industry, including positions as VP of Engineering and a leader of R&D and engineering teams. This resulted in the development of more than 60 products in various non-volatile memories. Andy is an accomplished technology visionary and inventor of more than 120 granted US patents. He performed research in the fields of neural networks and artificial intelligence while earning a master's degree in electrical, computer, and systems engineering from Rensselaer Polytechnic Institute in New York. He earned his bachelor's degree from the National Cheng Kung University in Taiwan. Title of the talk is New 3D AI Chip Technology Accelerating Generative AI. Please join me in welcoming Andy Su.
Generative AI has opened a whole new era for AI technology that is boosting entire industries with new applications like ChatGPT. These new applications run on AI chips using GPUs and high-bandwidth memories, and this makes them very expensive. Also, they consume a lot of power and generate a lot of heat, so data center expenses grow sky high. A new type of AI chip is needed, one that costs less, performs faster, and consumes less energy. The current AI chip architecture stores data in high-bandwidth memories and sends the data through data bus to GPU to perform AI algorithm. This architecture is not efficient. The data bus causes long delay and high power consumption. Semiconductor is developing a new type of HBM chip called 3D XAI that can directly perform AI processing using currents flowing through the memory cells. 3D XAI operates like a hardware neural network that eliminates the inefficiencies of current AI chip architecture caused by excessive data transfer between HBM and GPU. 3D XAI contains an 8,000 neuron circuit layer at the bottom to simulate the function of neurons and 300 memory layers on top to simulate synapses, which allows the chip to pre-process a large amount of data before sending it to GPU. This dramatically increases the entire AI chip's performance while reducing the power consumption that comes from excessive data transfer. Using 3D XAI chips can offer 100 times more performance, reduce power consumption by 99%, and boosts the memory density by 8 times. So our chip can process large model AI more efficiently and effectively. This makes 3D XAI a powerful solution to accelerate AI technology. 3D XAI, AI processing in 3D memory.
Hello everyone, my name is Andy Su. I'm the founder and CEO of Semiconductor. I'm excited to be here to talk with you about the hottest topic on Earth today, AI chips. AI chips took the center stage in this AI revolution that will reshape the entire world we live in today. Now, let's start the journey. AI is everywhere, and it is changing our lives in amazing ways. We use ChatGPT, Copilot, Gemini, and many more AI applications in our day-to-day lives. But how can AI do all of these wonderful things? Today, I'm going to show you how AI systems are created and operated from the inside. Do you know AI uses software and hardware to simulate a human brain's nervous system? Our brain contains 100 billion neurons and more than 100 trillion of interconnections called synapses. The neurons communicate with each other by using electrical signal flowing through the synapses. These synapses use chemical to store data called weights. And these weights determine how strong the electrical signal can pass through the synapses. So by storing different weights on a group of synapses, the electrical signal can be directed to the neurons to perform a specific task, like grabbing a cup or saying hello. This is how our brains learn things. And this specific group of the weights is called a model. Now, after we learn how our brains learn things, let's talk about how we build AI chips today to simulate this biological system. Today's AI chip uses simulation software to simulate this biological system. And this simulated virtual system is called artificial neural network. Artificial neural network contains multiple layers of neurons. Today's neural network may contain between tens to hundreds of layers, and each layer contains thousands to 10,000s of neurons. These neurons are interconnected by synapses, and each synapse can store data called weight. And since this system is virtual and simulated by the software, so there's no real signal flow. We have to use the software to calculate the data for each neuron and each synapse. Now, let me show you how the calculation is done. When the neuron in the first layer receives input data, the data will flow through multiple synapses to the neuron in the next layer. And the AI algorithm will multiply these inputs data with the weights stored in each synapse. This simulates how strong the signal can pass through the synapse in our biological system. Then the data will be summed and go through an activation function. The activation function will generate an output based on how strong the summed data is. So this simulates the function of the neuron. Then the activation function will send the output to the next layer of neurons. Now we finish the calculation for just the one neuron in one layer. This process will be repeated for all the neurons in the first layer, and then repeated for all the rest of the layers. Finally, it reaches the end to generate output data. Quite complicated, right? So the AI algorithm basically performed three functions: multiplication, accumulation, and activation. The first two functions, multiplication and accumulation, are also called MAC, which simulates the function of synapses. The activation simulates the function of neurons. So now we have built the mathematical algorithm to simulate the neural networks. By performing this algorithm, we can direct the signal flow to the specific neuron to use this artificial neural network to perform specific tasks. For example, we can direct the signal flow to recognize a specific image, like a dog, a cat, a bird, or a fish, just like our brains. Isn't this amazing? So we have talked about the software to simulate the neural networks. Now, we are going to talk about the hardware. Remember, both cannot live without each other. I'm sure you are familiar with the two components for AI chips, GPU and HBM. GPU stands for Graphic Processing Unit. HBM stands for High Bandwidth Memories. GPU and HBM performs data processing and data storage respectively. And HBM is used to store data for the models. GPU is used to process the data with AI algorithm to simulate neural networks. An AI chip normally contains one GPU and many HBM. Each HBM contains 12 to 16 DRAM chips. And these chips inside the HBM are interconnected by thousands of through-silicon vias, TSV. The more DRAM chips are used, the larger AI model can be stored and more powerful for the AI chips. As the data is stored in HBM to run AI algorithm, first, the data needs to be transferred from HBM to GPU through thousands of connections called the data bus. Then the GPU can run the AI algorithm to process this data. Now, let's look at what's inside the GPU. The GPU contains thousands of processing units called cores. Today's state-of-the-art GPU may contain more than 10,000 cores. These cores allow the GPU to parallel processing large amount of the data. And each core contains a lot of circuits called the multipliers to perform the multiplication functions. And lots of the circuit called the adders to perform the accumulation function. After data is transferred into the GPU, this circuit will process the data to simulate the neural network. Since this circuit occupies a large area of the chip, it makes the GPU very expensive. Now, let's touch on some of the challenges related to the current AI chips architecture. Neural networks model can be huge and requires an extremely number of the calculations. For example, for just the one neuron layer with 1,000 input and 1,000 output, it will require 1 million calculations based on the 1 million weights. So to perform just one layer of calculation, these 1 million weights need to be first transferred from HBM to GPU through the data bus. Therefore, the data bus bandwidth, which is about 1.2 terabytes per second today, becomes a bottleneck. Transferring such a huge amount of data across the data bus can cause a lot of delays, consumes lots of energy, and generate lots of heat. According to OpenAI, the energy bill for running just 1 day of ChatGPT cost almost $1 million. This means that soon enough, we may need to build nuclear power plants to run AI. Do you get how crazy this is? This problem kept me awake for many nights. And finally, all my sleepless nights led to what I believe is truly exceptional. Semiconductor presents 3D XAI chip. 3D XAI chip is targeted to replace the existing HBM chips to solve the bottleneck of the data bus and make the current AI chips more efficient and consume much less power. The new HBM using 3D XAI will contain 12 to 16 3D XAI chips connected by thousands of through-silicon vias called TSV. These 3D XAI chips are not traditional DRAM chips. They are not only for data storage. They are special DRAM chips that can perform AI processing inside the 3D memories. Now, let me show you the structure of a 3D XAI chip. Each 3D XAI chip contains 300 layers of memory cells to simulate a large number of the synapses. And in the bottom, it has a neuron layer which contains 1 kilobyte. It's about 8,000 neuron circuits to simulate the neurons. So this structure creates a hardware neural network to perform data storage and the data processing in the same chip. It can reduce the requirement of transferring all the data back and forth to GPU to perform the calculations. So it can dramatically reduce the power consumption and the heat generation caused by the data bus. How do we do that? The key element for 3D XAI chip is the 3D memory array. The traditional 2D or 3D DRAM cells cannot be used in this array because they use capacitors to store data. The data stored in the capacitor will be lost during the accumulation function. So we need a new type of 3D DRAM to implement this function. 3D XAI is based on Neo Semiconductor's 3D XDRAM technology, which is the world's first 3D NAND-like DRAM. It stores data in the floating body of the cell, so it does not require an extra capacitor. This makes the cell structure very simple and easier to manufacture. The cell structure is similar to today's 3D NAND flash memory. So it can be manufactured using the existing 3D NAND process with some modification. This greatly reduces the challenges and the development cost for this 3D XAI chip. The 300 memory layers can be manufactured all at once instead of layer by layer. So this dramatically reduces the manufacturing cost. According to our estimation, each 3D XAI chip can provide 128 gigabit capacity, which allows it to store 8 times larger model than today's HBM. And the data stored in the floating body will control the current flowing through the channel of the cell. In this way, the data stored in the floating body will not be lost during the operation. This makes it suitable for performing AI operations. When the cell is applied with the input data, it will generate a cell current based on the data stored in the cell. This operation can be used to perform the multiplication function for neural networks. Let me explain. When the input data is 1 and the sales data is 1, it will generate a current to represent the output data 1. If the input data is 0 or the sales data is 0, it will not generate a current, which represents data 0. So we can use the cell current to represent the multiplication function, the result for the input data and the sales data. This can be used for the AI operation. Now, let's apply the multiple input data to multiple cells. These cells will generate multiple cell current flowing to the B9 and form a sum of the currents. This operation can be used to perform the accumulation function for neural networks. By using this array, 3D XAI can directly use current to perform the multiplication and accumulation functions without using software to calculate the data for each synapse and each neuron. And with this array, we can apply thousands of the input data to the array to generate the currents for thousands of the outputs. This performs 1,000 times 1,000 operations for 1 million synapses. Then the current will be sent to the neuron circuit under the array to perform an activation function. We call this structure AI processing in 3D memory. Sounds cool, right? Compared with other in-memory computing solutions using analog memories, this array uses digital data, not make it compatible to today's GPU architecture. And to increase the accuracy, the thousands input can be divided into groups and fed into the array sequentially. This will achieve higher accuracy over other in-memory computing solutions. So, 3D XAI chip can use the memory array to perform multiplication and accumulation, and use the neuron circuit in the bottom to perform the activation. This architecture allows the huge models data to be processed inside the 3D memory. As a result, the memory layer can increase the density by 8 times. The neuron circuit can increase the performance by 100 times. And the in-memory processing can reduce 99% of the power consumption by the data bus. Now, let me show you how the neuron circuit works. The bottom neuron layer contains hundreds of the neuron circuit blocks. These blocks can transfer data back and forth with GPU through the 1,000 TSV bus. And each neuron block is connected to the memory array on top of the circuits. So inside each neuron block, there are hundreds of input neuron and output neuron circuits. The input neuron circuit can send input data to the memory array to perform the multiplication and accumulation functions. The output neuron circuit can receive current from the memory array to perform the activation functions. So since all the input neuron and the output neurons can process the data in parallel, it can achieve very high data processing throughput. According to our estimation, each 3D XAI chip can contain 1 kilobyte of neuron and process 10 terabytes of data in 1 second. For HBM using 12 3D XAI chip, it can process 120 terabytes of data in 1 second, which is 100 times more data throughput than using today's HBM. Now, let me tell you how our chip performance is much better than other processing in memory solutions in the market. You can see the difference between the number of neuron circuits. Other processing in memory solution has 16 processing units in one chip. So it can simulate only 16 neurons, while Neo's chip can simulate 8,000 neurons. So its performance will be hundreds of times higher than other processing in memory solutions available in the market today. Now, let's compare the entire AI chip's performance. The current AI chip architecture stores data in HBM and relies on GPU to perform all calculations. This separated data storage and the data processing architecture makes the data bus unavoidably to be the bottleneck of the performance. So even more advanced GPU, TPU, or NPU are used. All of these AI chips' performance will be limited by the data bus bandwidth. By replacing the current HBM with 3D AI chip, the new HBM can pre-process 100 times more data before it sends the output data to the GPU. This can remove the data bus bottleneck and unleash the full potential of the GPU. It can also reduce the amount of data transferred through the data bus and therefore reduce the power consumption. So, replacing HBM with 3D AI chip can dramatically boost the AI chip performance by 100 times, reduce 99% of the power consumption caused by data bus, and store the 8 times larger AI models than today's HBM. Did you ever imagine something like this can happen in the near future? I'm happy to report Neo Semiconductor is already working on silicon proof of the concept for this amazing technology. And I'm looking forward to sharing our progress with you soon. It was my pleasure being here today, and I look forward to chatting more at our stunning booth, 507. Thank you very much.